Hey everyone, and welcome back. Today, we're jumping headfirst into something that's totally changing the world of software development. We're talking about building truly intelligent AI applications, going way beyond a simple chatbot interface, exploring what it really takes to create AI that's robust, reliable, and can actually scale. You've probably played around with something like ChatGPT, right?
hmm
But building serious production-grade AI, that's a whole different ballgame. It really requires mastering a new stack of foundational technologies, and that's exactly what we're going to unpack for you today in this deep dive.
Yeah, and what's truly striking here is just how much the game has changed.
Yeah.
It's fundamental. We're going to break down the three core pillars of this new AI stack and then show you how they all kind of snap together, how you build these powerful systems that can actually reason, access external knowledge, and, interact with the world in pretty sophisticated ways.
And we've distilled insights from some really comprehensive guides, including the developer's playbook, Mastering Production Grade AI. Basically, trying to give you a shortcut to understanding this, let's be honest, pretty complex space. Think of it as your essential guide, not just the what, but really the why and the how of building AI that actually works. So what does this all mean for you? Maybe you're prepping for a meeting or trying to catch up on this whole field, or maybe you're just insanely curious. By the end of this deep dive, you won't just understand the core pieces, but you'll also get a real sense of the challenges and the solutions for deploying AI that truly delivers value.
Right, and that brings up a fascinating question, really. How do we empower these huge language models? How do we get them beyond just their static training data?
Yeah.
It all starts fundamentally with understanding how we talk to them effectively.
Okay, let's dig into that. The first foundational pillar, prompt engineering. It sounds like a buzzword, maybe, but it really feels like an art and a science, doesn't it? Because getting it wrong,
Mhm.
well, it can make your super smart AI seem not so smart after all.
Absolutely. Prompt engineering is fundamentally about designing and optimizing those inputs you give to an LLM.
Mhm.
You're trying to get the most accurate, the most relevant, and ultimately the most useful responses back.
Yeah.
It's your main lever for controlling how the model behaves. And, one of the most common failure points, surprisingly, is just ambiguity. Simple lack of clarity.
How so?
Well, think about it. If you ask something generic like, tell me about artificial intelligence,
Mhm.
what do you get?
Yeah.
Very broad, probably not a very useful answer.
Hmm.
But if you ask, explain the main differences between supervised and unsupervised machine learning, focusing on data labeling requirements and common use cases.
Yeah.
Now, the model knows exactly what you want.
Right, you're giving it guardrails, specificity.
Exactly. Specificity.
Yeah.
And context is huge, too, just like with people, right? LLMs perform much better when they have context.
Well.
Think about asking if I'm sorry and my bad mean the same thing. Usually, yeah.
Hmm.
But add the context of being at a funeral, suddenly the answer changes drastically.
Wow, yeah. Good point.
So for AI, this means giving it domain information, maybe user history, situational details, anything that helps narrow down the possibilities.
Yeah.
And another really powerful technique, a best practice really, is framing instructions positively.
What do you mean by positively?
Instead of telling it what not to do, like do not ask for interests, which can be confusing, you specify what it should do, like the agent is responsible for recommending a movie from the top global trending movies. It should refrain from asking users for their preferences.
Mm.
See, it's much clearer. It guides the model much more effectively.
Okay, so positive framing. Be specific. Give context.
Right. And remember, it's an empirical science. You don't just write one prompt and you're done. You start simple, you look at the output, you refine it. It's this constant iterative feedback loop. You're always learning and adjusting.
That makes sense. Trial and error, basically.
Right. A lot of it, yeah. Especially when you need that consistency for production applications. Reliability is key. And that's precisely where structured prompting comes into play. It's about enforcing a specific output format. You're essentially turning the prompt into a kind of script that the LLM has to follow.
A script. How does that work in practice?
Well, JSON is used all the time for this. You can literally instruct the LLM to produce a JSON object that follows a specific schema you define. So for sentiment analysis, you might say output JSON with keys, sentiment, product, features. We've even seen Python examples defining that schema right in the prompt itself.
Okay, so you're programming the output format.
Pretty much. And major LLM providers are also really pushing the use of XML tags now. Things like instructions or context. Why? Because they offer these really robust, unambiguous ways to separate different parts of a complex prompt. It makes them incredibly reliable, especially for intricate tasks.
So it's almost like you're giving the LLM a really precise blueprint. You're turning it from just a chat partner into a reliable, consistent colleague. That's the real game changer for putting these things into production, isn't it?
Precisely. A really well-designed structured prompt usually has a few key parts. You've got the main instruction, obviously,
Yeah.
relevant context, the actual user input, sometimes optional examples, that's few-shot learning, maybe a persona for the LLM to adopt, and a clear output indicator specifying the format.
Okay, structured prompting gets us reliability, but here's where I think it gets really interesting. Advanced prompting. You mentioned it's not just telling the model what to do, but teaching it how to think. What does that look like?
Exactly. These advanced techniques unlock much more complex, multi-step problem solving. It's pretty amazing. Take chain of thought prompting, or COT. The idea is to encourage the model to break down problems into intermediate reasoning steps. It mimics how humans think through something complex.
Showing its work.
Showing its work.
Yeah.
Exactly. This ability tends to show up in the really large models, typically over 100 billion parameters.
Hmm.
And you can trigger it a couple ways. Few shot, where you show examples with the steps laid out, or surprisingly effectively sometimes, zero shot. Just adding a simple phrase like, let's think step by step to your query can work wonders.
Just adding that phrase. That's it.
Often, yeah, sort of nudges the model into demonstrating that logical, sequential thought process, forces it to show its work, like you said. Then there's another really powerful one, react. Stands for reasoning and acting.
Reasoning and acting.
It
Okay.
has this incredible synergy. It enables the LLM to generate both its internal thoughts and specific actions it needs to take. Things like making API calls or doing web searches.
Whoa, okay. So it can do things.
It can do things. It operates on this dynamic loop. The model thinks, figures out what it needs to know or do, decides on an action, like a search query. It performs the action, gets an observation back the search results, for instance. Then it thinks again based on that new information. And this loop continues until the problem is solved.
That's incredible. So React essentially gives the LLM the ability to fact check itself in real time by using external tools. That seems huge for cutting down on those, frustrating hallucinations or making stuff up.
It is huge. That's one of its most revolutionary aspects,
Mm-hmm.
grounding and enhancing factuality.
Mm-hmm.
It lets the model augment its internal static knowledge with real-time external information. That significantly mitigates hallucination. It can even perform multiple searches, multiple actions to answer complex questions that require information from different sources. Multi-hop questions, just like a human researcher might tackle a task.
That's incredibly powerful for accuracy, definitely. But does that dynamic loop think, action, observe, think again, does that add a lot of extra time, latency? How do you balance that performance trade-off in a real application?
That's a critical production challenge. You're absolutely right. Yes, the multi-step nature of React can introduce latency. Each action often involves an external call, which takes time. So the balance comes from a few things. Optimizing the tools it calls, maybe caching observations if they're likely to be needed again soon, and using React strategically. You wouldn't use it for every single simple query. You reserve it for tasks that genuinely need that external grounding and complex reasoning. It's always a trade-off, weighing the cost of that extra latency against the huge benefit of factual accuracy and reduced hallucination for your specific application.
Okay, so the prompt itself becomes less of a simple instruction and more like a mini program. And the developer is like an architect designing these cognitive workflows. We've seen how prompts help LLMs understand what to do, but to really unleash their power, they need to understand meaning itself, right? That seems to be where this idea of embeddings totally changed the game. Why are they called the language of AI?
Yeah, that's a great way to put it. They really are the bridge, the connection between our human language with all its nuance and messiness and the cold, hard mathematics that computers understand.
Mm-hmm.
An embedding is essentially a numerical representation. A list of numbers, a vector, can represent a word, a sentence, an image, even a whole document. And the key characteristic, the magic, is that things with similar meanings end up having vectors that are numerically close together in this high-dimensional space.
High-dimensional space. Sounds complicated.
It just means lots of numbers in the list. But think of it conceptually. The vector for king and the vector for queen will be much closer mathematically than the vectors for king and, say, gabbage.
Okay, got it. Similarity equals closeness.
Exactly. This mathematical representation of meaning is what lets AI models compare things, search through vast amounts of unstructured data, and even reason about it with incredible nuance.
So how do these embedding models actually create these vectors?
Well, it starts with tokenizing the input, breaking text down into smaller chunks like words or parts of words. Then the model extracts complex features from those tokens and their context. And finally, it compresses all that information into a dense vector, usually a few hundred, maybe a few thousand numbers long. And modern models, especially the transformer-based ones like BERT, are really good at understanding context. They'll create different embeddings for the word play, depending on whether you say, I went to a play or I like to play baseball. Capturing those distinct meanings is key.
Okay, so embeddings are crucial. What are the big decisions you face when you actually need to choose an embedding model for your project? You mentioned proprietary versus open source. What's the real trade-off there, beyond just the sticker price?
That is truly one of the most consequential decisions in your whole AI stack. It impacts everything downstream. So proprietary APIs, like the ones from OpenAI, they are exceptionally easy to use. That's their big draw.
Plug and play, almost.
Pretty much. No infrastructure for you to manage. They're constantly updated by the provider. Simple API calls. Fantastic for getting started quickly, for rapid prototyping.
Yeah.
But the downsides are real. Cost is one. Yeah. It's usually priced per token, so if you're bidding millions of documents, it adds up fast. And maybe more critically for some, data privacy and retention can be issues. Your data is passing through their systems.
Right, if you have sensitive internal documents.
Exactly. Plus, they're black boxes. You have limited customization. You can't fine-tune them on your own specific jargon or domain data. Now, models like OpenAI's text embedding -3 small and large are very strong performers. And they do offer a need dimensions parameter now, letting you trade off a bit of performance for lower cost by using smaller vectors. That's a nice touch.
Okay, so ease of use, but potential cost and data concerns. What about the open source side? From places like Hugging Face.
Open source models offer some powerful advantages. The big one is often cost effectiveness, especially at scale, because you're not paying per token. You also get complete control and enhanced data privacy because you self-host them. Your data stays within your environment.
And you can tweak them.
Yes. You can fine-tune them on your own domain-specific data. If you work in a field like medicine or law with very specific language, fine-tuning can give you significantly better performance than a general-purpose model. The trade-off. Well, it requires real ML engineering resources. You need people who know how to deploy, manage, and maintain these models, plus the compute infrastructure, often GPUs. It's more work up front.
So it's an investment.
It's an investment, but top open-source models like BAII's BGM3 or Microsoft's multilingual E5 Large often perform just as well, or sometimes even better, than proprietary APIs on standard benchmarks like MTB.
So this choice isn't minor at all. It's a core architectural decision.
Absolutely, it's an architectural linchpin. The vector dimensionality, how many numbers are in each embedding, directly impacts your storage needs and the computation required for search later on.
Right.
And API versus self-hosted fundamentally changes your operational footprint, your MLOps complexity, plus the model's actual performance on your data in your specific domain that sets the quality ceiling for your entire application. It's a big decision.
Okay, so we've taken our documents, our text, maybe even images, and turned them into these meaningful numerical vectors using an embedding model. But now we have potentially billions of these vectors, storing them and searching through them incredibly quickly. That's where the next piece comes in, the vector store or vector database.
Yeah.
Why can't we just use a regular database for this, like SQL or something? It feels like it's just data, right?
That's a great question, and it gets to the heart of why vector databases exist. Traditional databases, like relational databases, are optimized for structured data and exact match queries. Think select from users where ED-GILS 123. They find perfect matches based on predefined fields. They are fundamentally ill-equipped for efficient, high-dimensional similarity search.
Why not?
Trying to find the closest vectors to a query vector in a traditional database would mean comparing your query vector to every single other vector in the database.
Oh, wow. Billions of comparisons.
Exactly. It's computationally infeasible at any meaningful scale. It would be incredibly slow. Like trying to find a specific shade of blue paint in a giant warehouse by looking at every single paint can one by one. Just doesn't work.
Okay, so we need a specialized tool. What makes a vector store different?
A vector store is a database purpose-built for storing and retrieving data based on its vector representation. That's its core job. So its key functionalities are storing these high-dimensional embeddings, often alongside the original data or metadata so you know what the vector represents, and performing similarity search using specialized algorithms.
Specialized algorithms.
Right. The engine that makes this possible at massive scale is called Approximate Nearest Neighbor Search, or ANN.
Approximate. Does that mean it's not accurate?
It means it trades a tiny, often negligible amount of perfect accuracy for massive gains in speed. It's about finding vectors that are very likely the closest, extremely fast. Instead of guaranteeing the absolute closest, it guarantees finding neighbors that are close enough for most practical purposes, but orders of magnitude faster.
Okay, speed versus perfect precision. Makes sense for many use cases.
Exactly. And the most popular and effective ANN algorithm used in many vector stores today is HNSW. It stands for Hierarchical Navigable Small World. It's a clever way of organizing the vectors into a multi-layered graph structure. Think of it like creating express lanes and local roads for navigating the vector space. It allows for incredibly fast searching without checking every single point.
Like a really efficient library index system for meaning.
That's a great analogy. It lets you quickly zoom in from a broad topic to a very specific concept without scanning every shelf.
So there seem to be a lot of vector store options popping up now. How do you choose one that's ready for production? It sounds like there might be similar trade-offs to the embedding models, convenience versus control.
You absolutely nailed it. The trade-offs are very similar. Key decision factors really boil down to a few things. First, the deployment model. Do you want a fully managed cloud service like Pinecone, where they handle all the infrastructure and scaling for you? Or do you prefer an open source option like Milvus or Weaviate that you host and manage yourself?
Okay, managed versus self-hosted. Big difference in operation.
Huge difference. Then, scalability. Can the database handle the number of vectors you anticipate, potentially millions or even billions? Performance is critical too. What's the query latency?
Yeah.
What are the recall metrics, meaning how often does it find the truly relevant items? And then you look at advanced features. Do you need sophisticated metadata filtering alongside the vector search? Do you need hybrid search capabilities?
Can you give us a quick rundown of some of the main players?
Sure, Pinecone is a popular choice, fully managed, very high performance, enterprise-grade features. Easy to use, but generally comes at a higher cost and offers less customization. Great if you want to minimize operational headaches. Weaviate is another strong contender. It's open source, but also offers a managed cloud version. It really excels at hybrid search, has a flexible data schema, and uses a GraphQL API, which some developers like. Maybe a slightly steeper learning curve than Pinecone. Milvus is a powerhouse for scalability. It's cloud-native, open source, highly configurable, supports GPUs for indexing. But being self-hosted, it comes with higher operational complexity. Qdrent is another open source option, written in Rust, known for its performance, memory efficiency, and advanced filtering capabilities. Chroma is often mentioned. It's more lightweight, very developer-friendly open source, excellent for getting started, prototyping, maybe smaller projects, but it might lack some of the heavy-duty enterprise features of the others. And one important note about Face, it's not actually a full database. It's a highly optimized library from Meta for doing the ANN search.
It's incredibly fast, but you have to build all the surrounding database infrastructure yourself, storage, metadata handling, APIs.
Right, so FAS is more of a component you'd build into your own system.
Exactly. So again, you're trading off the ease and features of a managed service against the control, potential cost savings, and customization of self-hosting an open source solution.
Ah.
But the key takeaway is that the vector database is becoming this essential new piece of the modern data stack. It's the data warehouse, but for the semantic meaning locked inside an organization's unstructured knowledge.
Okay, this is great. We've got our prompt engineering down, we understand embeddings and how they capture meaning, and we have these specialized vector stores to search them lightning fast. Now, how do we actually stitch all of this together to build those truly intelligent applications we talked about at the start? This seems to be where RAG, Retrieval-Augmented Generation, really comes into its own. Why has RAG become such an industry standard for production AI?
RAG is an absolute game changer. Seriously, because it directly tackles some of the most critical limitations of standalone large language models. First, and maybe most obviously, it gives LLMs access to fresh and external information. It overcomes that whole static training data problem where the model only knows things up to a certain point in time.
Right, so it can talk about current events or use up-to-date company info.
Exactly. Second, it provides factual grounding. This is huge. It significantly reduces the tendency of LLMs to hallucinate or just make things up. Why? Because the answers are based on actual information retrieved from your knowledge base. Verifiable facts.
That's massive for trust and reliability.
Massive. And third, it's a remarkably cost-effective way to make the LLM knowledgeable about specific domains or proprietary information. Think about your company's internal documents, technical manuals, legal contracts. Instead of having to do expensive fine-tuning of the base LLM itself, you just load that info into your RAG system's knowledge base.
So cheaper and faster way to get domain expertise into the AI.
Much cheaper and faster. Generally, yes.
Okay, so RAG sounds incredibly useful. What does a RAG system actually look like at a high level? How does it operate day to day?
It basically operates in two distinct phases. Think of it as prep time and game time. First, you have the indexing pipeline. This is mostly an offline preparatory stage. This is where you take all your documents, your knowledge sources, load them, clean them up, chunk them into manageable pieces.
Chunking, right, that critical step.
That critical step. Then you convert those chunks into the embeddings we talked about, and you store those embeddings and maybe the original text in your vector database. That's the prep work.
Yeah.
Indexing.
Got it. Building the knowledge library.
Exactly. Then, second, you have the retrieval and generation pipeline. This is the online part, happening at runtime whenever a user asks a question. The user's query comes in. It also gets embedded using the same model. That query embedding is then used to search the vector store to find the most similar, most relevant chunks of text from your knowledge base.
Okay, finding the right pages in the library.
Perfect analogy. These retrieved chunks, they act as context. They're combined with the user's original query, maybe formatted nicely in a prompt, and then the whole package is passed to the LLM, and the LLM uses that specific retrieved context to generate a truly context-aware, factually grounded answer.
Brilliant. So it retrieves first, then generates based on what it found.
Precisely. Retrieval, then augmented generation, RAOH.
Let's dive into that indexing pipeline a bit more. What are the key steps to really prepare your knowledge base so it's actually useful and not just, a digital junk drawer?
Good question, because data quality is paramount here. Step one is loading and pre-processing. This means ingesting your source data. It could be from web pages, maybe using something like a web-based loader, or PDFs, Word docs, your internal wiki, maybe even Slack messages or support tickets. And cleaning this raw content is really crucial for production systems. You need to remove noise, things like HTML tags, navigation bars, ads, irrelevant boilerplate text, maybe extra white space. Get it down to the actual meaningful content.
Okay, load and clean. What's next?
Next comes chunking. And I can't emphasize this enough. This is arguably the most critical step in the entire indexing process for RDED performance.
Why is chunking so vital?
Two main reasons. First, LLMs have finite context windows. You can't just stuff a 100-page document into the prompt. Second, and perhaps more subtly, trying to create a single embedding for a very large, diverse document results in a blurry or averaged vector. It doesn't represent any specific concept within the document very well.
Ah, so it loses the specific details needed for good retrieval.
Exactly. Chunking creates smaller, focused, semantically coherent units. Each chunk represents a more specific idea, leading to much better, more precise retrieval later on.
I remember an early project where we skipped careful chunking. We just fed entire legal documents to the LLM. The answers were, well, let's just say they wouldn't hold up in court.
I believe it. That's when you truly appreciate the magic of good chunking.
So how do you chunk effectively?
A highly recommended strategy is recursive character chunking.
Yeah.
It's clever because it tries to split the text along natural semantic boundaries first, like paragraphs. If a chunk is still too big, it tries splitting by sentences. Still too big, it splits by words. It tries to keep related text together as much as possible. We also generally recommend using a small overlap between chunks, maybe 10–20% of the chunk size.
Overlap. Why?
It helps preserve context across boundaries. If a sentence or idea starts at the very end of one chunk and finishes at the beginning of the next, that overlap ensures the LLM can still see the full thought when processing adjacent retrieved chunks.
Smart. Okay, load, clean chunk carefully with overlap. Then what?
Then, finally, you embed and store these chunks. You generate the vector embeddings for each chunk, maybe using a model like OpenAI's Text Embedding 3 Small or your chosen open source model. And then you load these embeddings, along with the original text chunk and any useful metadata, like the source document name, page number, etc., into your chosen vector store. For prototyping, like we said, a lightweight option like Chroma is great and easy to set up.
Okay, so now our knowledge base is indexed. It's loaded, cleaned, chunked, embedded, and stored in the vector database. Ready to go. How does the retrieval and generation pipeline work at runtime? When a user actually asks a question, what happens step by step?
Right, this is the live part. The core logic usually involves building what's often called a RAG chain or pipeline. First, you need a retriever. You typically create this directly from your vector store instance. The retriever's job is simple. You give it a query, or query embedding, and it returns the most relevant documents or chunks based on similarity search.
Okay, the search mechanism.
Exactly. Next, you define a prompt template. This isn't just a simple question, it's structured. It has specific placeholders, usually for context where the retrieved document chunks will go, and question where the user's original query goes. It might also include instructions like, answer the question based only on the provided context.
Guiding the LLM to stick to the facts found.
Precisely. Finally, you chain these components together. the retriever, the prompt template, and an LLM like GPT-4o or Claude 3. Frameworks make this chaining easier. When you invoke this chain with the user's question, it automatically orchestrates the whole flow. It takes a question, sends it to the retriever searches the vector store, gets back the relevant chunks. Those chunks are plugged into the context placeholder in your prompt template. The user's question goes into the question placeholder. That fully formatted prompt is then sent to the LLM, and the LLM generates the final context-aware answer based on everything it received. It's a seamless flow from search to synthesis.
That makes sense. It connects the pieces logically. Now, many developers, especially when they're starting out, hear about frameworks like LangChain and Lemma-Index. What's the deal there? Are they basically the same thing, or do they serve different purposes in building these REG systems?
That's a very common question, and they're definitely not interchangeable. They have different philosophies and strengths. LangChain is best thought of as a general-purpose, highly modular framework for building any kind of LLM application. It's not just for RAG. It focuses on flexibility and composability. It uses concepts like chains and its own language expression language, LCEL, to let you connect lots of different components together. LLMs, tools, retrievers, parsers, memory.
So like a big box of Lego bricks for building anything AI related.
That's a great analogy. It's ideal if you're building complex, maybe agentic systems where RAG is just one tool among many that an AI agent might use. It gives you very granular control.
Okay, LangChain is the general toolkit.
Yeah.
What about Lemma-Index?
Lemma-Index, on the other hand, was specifically designed and optimized for RAG. That's its primary focus. It prioritizes ease of use and provides powerful, high-level abstractions specifically for the tasks involved in RAG-K. Data ingestion, indexing, and querying knowledge bases. It really excels at the data indexing part and comes with many advanced built-in querying strategies and index types that can help you get to a high-performing RAG system quickly, often with less boilerplate code for the core RAG functionality itself.
So if my main goal is building a really smart search or Q&A system over my documents, Lemma-Index might be the faster path to get something effective working.
Generally, yes. If your core task is powerful search and retrieval over a knowledge base and you want to leverage sophisticated built-in RAG strategies quickly, Lemma-Index is often a great choice.
But if I'm building, say, a multi-tool AI assistant that needs to browse the web, run code, and query internal documents using RAG, maybe LangChain's flexibility is better.
Exactly. If RAG is just one component in a larger, more general-purpose LLM application, and you need maximum flexibility, granular control, and the ability to easily chain various tools and models together, LangChain's modularity is probably a better fit.
Yep.
But the key insight here really is that these frameworks are ultimately scaffolding. They help you build faster. The real goal should be to master the fundamental principles of RAG itself: chunking, embedding, retrieval, prompting. Understanding those lets you open the black box of the framework when needed, allowing for the deeper optimization and customization required for true production-level performance, regardless of which framework you started with.
That's a great point. Don't just learn the tool, learn the principles behind the tool.
Precisely.
Okay, so building a prototype RAG system might seem straightforward enough with these frameworks, but taking it to production, dealing with real-world traffic, diverse user queries, maybe constantly changing data, that feels like a whole other level. What are the hard parts when you move beyond that initial proof of concept or demo?
You're right. Production introduces a whole new set of challenges. Things that might not have been obvious in a prototype suddenly become critical. We're talking about really nailing accuracy, managing performance and latency, controlling costs, and perhaps most importantly, setting up robust and continuous evaluation. These are the areas where RAG projects often hit bumps.
Let's start with accuracy then. We've done our basic chunking, we've got our embeddings, we're doing similarity search, but you mentioned earlier that naive vector search isn't always perfect. How do we make retrieval even better? Especially when simple similarity might miss important keywords or pull back stuff that's only vaguely related.
Yeah, naive vector similarity search, while powerful, definitely has limitations. It can sometimes struggle with queries that rely heavily on specific keywords, not just semantic meaning. And it can suffer from the lost in the middle problem. Relevant information might be in a retrieved chunk, but it gets buried among less relevant sentences, confusing the LLM later. So we use more advanced techniques to significantly boost precision and recall. One major one is hybrid search.
Hybrid search, combining different approaches.
Exactly. It combines the semantic vector search we've been talking about with traditional keyword-based search methods, think classic text matching, often using algorithms like BM25, which is common in search engines like Elasticsearch. You run both searches, semantic and keyword, in parallel for a given query. Then you intelligently merge the results from both lists.
How do you merge them intelligently?
A common technique is reciprocal rank fusion, or RRF. It looks at the rank of each document in both lists and gives higher scores to documents that rank well in both searches. This makes the system robust to a wider variety of queries, ones that are purely semantic, purely keyword-based, or a mix.
Okay, so hybrid search gets you the best of both worlds. But are there times when just throwing keyword results in could actually add more noise or irrelevant stuff if you're not careful?
That's a great point, and yes, it could, if done naively. Just taking the top end from each and mushing them together might not be optimal. That's why the fusion step, like using RRF, is so important. It intelligently combines the rankings, prioritizing items that both methods agree are relevant. It's not just a simple union of the two result sets.
Got it. So hybrid search is one technique. What else?
Another really impactful technique is re-ranking. Think of it as a second, more precise filtering stage after the initial retrieval. So your first retrieval step, maybe using hybrid search, is designed to be fast and cast a relatively walled net, retrieving maybe the top 50 or 100 potential candidates. Get high recall. Then you pass these candidates to a second, more powerful but computationally more expensive re-ranking model.
A different model.
Often, yes. These are typically cross-encoder models. Unlike the embedding models, which process the query and document separately, a cross-encoder looks at the query and the full text of a candidate document together.
Yeah, so it gets more context for relevance.
Much more context. This joint processing allows for a much deeper, more nuanced analysis of relevance. It's very effective at pushing the truly best results to the very top. Models like Cohere's re-rankers or open source ones like Mex by Re-rank are excellent for this stage. It significantly improves precision.
So fast retrieval first, then a slower, more accurate re-ranker on a smaller set. Clever.
Exactly. And a third category of techniques involves query transformations. Here, the idea is to use an LLM itself to improve the user's query before you even send it to the retriever. Better input leads to better output.
Using an LLM to rewrite the query, how does that?
Several ways. Multi-query is one. The LLM generates several different versions or variations of the user's original query, hoping that one of them will be a better match for relevant documents. You retrieve results for all variations. Step-back prompting is another. If the user asks a very specific, complex question, the LLM first generates a higher-level, more general question. Retrieving documents for this broader question can provide useful context that the LLM needs to answer the original specific one. And then there's high DE, hypothetical document embeddings. This one's neat. The LLM generates a hypothetical ideal answer to the user's question first. Just makes up a plausible answer.
It makes up an answer.
Yes. Then you embed that hypothetical answer and use its embedding to search the vector store. The idea is that the embedding of a perfect answer is often semantically closer to the embeddings of the actual relevant documents than the embedding of the original, maybe ambiguous question.
Wow, that's counterintuitive but sounds powerful. So, hybrid search, re-ranking, query transformations, lots of tools to improve accuracy. What about the other production headaches? Scaling this up, managing costs, handling all the operational stuff that keeps engineers up at night.
Right, accuracy is just one piece. Operationally, scaling is huge. For scalability and performance, you almost certainly need to move beyond those lightweight local vector stores like Chroma used for prototyping. You need distributed, scalable systems like Pinecone managed or self-hosted Weaviate or Milvus to handle potentially millions or billions of vectors efficiently. Latency management becomes critical too, especially for user-facing applications where users expect fast responses.
How do you manage latency in RG?
Several strategies. Caching is essential. Caching final LLM responses for common queries. Caching frequently retrieved document chunks. Batching multiple user queries together before sending them to the LLM can improve throughput. And optimizing your infrastructure using distributed systems effectively, ensuring data locality so compute is close to storage, all help shave off milliseconds.
Okay, scaling and speed. What about the data itself? In production, knowledge isn't static.
Exactly. Robust data management is key. Production knowledge bases are rarely static. New documents get added, existing ones get updated or deleted, so you need dynamic data pipelines. You can't just manually reindex everything once a month. Often this means using event-driven architectures, maybe using tools like Apache Kafka or Cloud Pub Sub services. When a document changes, an event triggers a pipeline that automatically updates the relevant chunks and embeddings in your vector store in near real time.
Keeping the knowledge fresh automatically.
Right. And data quality, again, is paramount. Garbage in, garbage out is brutally true for RAG. You need rigorous processes for cleaning source documents, removing duplicates, filtering out noise before it even gets into your vector store and pollutes your retrieval results.
Makes sense. And what about the elephant in the room cost? These systems use powerful embedding models, LLMs, vector databases. It sounds expensive.
Cost optimization is definitely a major consideration in production. It requires a multi-pronged approach. Efficient data management helps using data compression features in vector databases, maybe implementing tiered storage where less frequently accessed vectors are kept in cheaper storage. Smart model usage is crucial. You don't necessarily need your most powerful, expensive LLM for every single step. Maybe use smaller, faster LLMs for intermediate tasks like query classification or simple query transformations, and reserve the big model only for the final answer generation. Prompt caching, like response caching, saves API calls and money. Using the right tool for the right job, cost-wise. Exactly. And if you're self-hosting the embedding models or vector database, then optimizing resource allocation becomes key. Using energy-efficient hardware, exploring techniques like model pruning or quantization to run models on less expensive hardware, these can drastically reduce your operational costs over time.
Okay, so there's a lot involved in taking RJAG from prototype to production. Accuracy, performance, data management, cost. This raises a really important question. Given all this complexity, how do you actually know if your ARC system is any good? How do you rigorously evaluate it beyond just trying a few queries yourself?
That is such a critical point. Evaluation isn't something you tack on at the end. It needs to be a continuous process deeply integrated into your development lifecycle. Because the simple truth is, you absolutely cannot systematically improve what you do not measure. You need metrics.
So where do you start with evaluation?
The foundation is creating a high-quality test dataset, often called a golden dataset. This should be a representative set of questions that your users are likely to ask, along with the corresponding ground truth answers, or perhaps more importantly for RAG, the specific documents or chunks that should be retrieved to answer those questions correctly.
Who creates this golden data set?
Ideally, you involve domain experts who really understand the subject matter. They can formulate realistic questions and identify the truly relevant source documents. LLMs can actually help generate candidate questions and answers, but human review and curation of that dataset is absolutely essential to ensure its quality and reliability.
Okay, so you have your golden data set. How do you use it to evaluate the REG system?
We typically evaluate the REG pipeline using a two-part framework. This is really important for diagnosing problems effectively. You assess the retrieval part and the generation part independently.
Separating search from synthesis.
Exactly. First, retrieval component evaluation. Did we retrieve the right documents? Forget the LLM's answer for a moment. Just look at the chunks the retriever pulled back. We measure this with metrics like hit rate. Did we get at least one relevant document in the top 2 results? Say top 5. Recall at higher K, what proportion of all the known relevant documents for that question did we manage to retrieve in the top K? And mean reciprocal rank, MRR, which measures how high up the list the first relevant document appeared. Higher is better.
Okay, so metrics focus purely on the quality of the search results.
Right. Then second, generation component evaluation. Given the documents that were retrieved, sometimes we force feed the known correct documents for this part, did the LLM generate a good answer? Here, the most crucial RAG-specific metric is faithfulness or groundedness. Does the generated answer stick only to the information present in the provided context documents? This directly measures hallucination within the RAG context.
Checking if it made stuff up based on the retrieved facts.
Exactly. We also evaluate answer relevancy. Is the answer actually relevant to the original user question? And answer correctness, how accurate is the answer when compared to the ground truth answer in our golden data set?
Okay, so specific metrics for retrieval and specific metrics for generation quality and faithfulness.
Correct. And there are practical tools and frameworks that help automate calculating these metrics, like Ragus and DeepEvil. They can run your golden dataset questions through the pipeline and compute these scores automatically.
What about using AI to evaluate AI? Can you use an LLM to judge the quality?
Yes, that's becoming increasingly common and powerful. It's often called LLM as judge. You can use a strong LLM, like GPT-4 or Claude 3 Opus, as an automated evaluator. You give it the original question, the retrieved context, the generated answer, and clear criteria, like faithfulness, relevance. You prompt it carefully, maybe even asking it to use chain of thought reasoning to explain its score, and it can produce surprisingly reliable quality scores, especially for metrics like faithfulness and relevance. It helps scale evaluation significantly.
But given all these amazing automated metrics and LLM judges, is there still a significant human element needed in ROI evaluation? Or are we truly at a point where automated methods are sufficient for most cases?
That's a fantastic question, and it really touches on a current frontier in MLOps for LLMs.
Mm.
While LLM as judge is incredibly powerful for scaling up evaluation running hundreds or thousands of test cases automatically, it's generally not seen as a complete replacement for human review yet, especially not for highly sensitive, high-stakes, or very nuanced domains.
Why not?
Well, LLMs evaluating other LLMs can sometimes be subtly biased by the generated answer itself,
Mm.
or they might miss subtle factual errors or context-specific nuances that a human domain expert would catch instantly.
Yeah.
Their understanding isn't the same as human understanding.
So, not quite foolproof.
Not quite foolproof. No.
Yeah.
Think of LLM as judge as a highly effective first pass. It's great for catching common failure modes, tracking trends over time as you make changes, and identifying areas needing closer inspection. It allows your human experts to focus their valuable time on the trickiest edge cases, the most ambiguous results, or the highest risk scenarios where accuracy is absolutely paramount.
So, automated for breadth, human for depth, and critical checks.
That's a great way to put it. And this whole separate evaluation of retrieval versus generation provides crucial diagnostic clarity. If your overall ROI quality drops, you can quickly pinpoint whether the problem lies in your chunking strategy, your embedding model, the retrieval algorithm, the re-ranker, or the final generator LLM itself. You know where to focus your improvement efforts.
Wow, what a journey, seriously. From understanding those fundamental building blocks, prompt engineering, embeddings, vector stores, to actually building a functional RI system, and then all the complexities of hardening it for the real demands of production. That was truly a deep dive into this modern AI stack.
It's just wild to think how quickly this field is moving, isn't it? I
Yep.
mean, just a couple of years ago, some of these concepts like advanced RI techniques were still pretty much bleeding edge research. And now they're rapidly becoming standard parts of a developer's everyday toolkit.
It really is incredible. And if you connect this back to the bigger picture, like you said, it's clear that the developer's role itself is evolving significantly. It's shifting. It's no longer just about writing explicit line-by-line code in the traditional sense. It's increasingly becoming the role of an AI systems architect. You're designing these complex cognitive workflows, you're curating and structuring knowledge bases, you're orchestrating interactions between different AI components. It's much more about system design and knowledge engineering now. Yeah. Architecting intelligence almost. And for you, the listener, this means a pretty significant expansion of your toolkit is needed, right? These skills prompt engineering, understanding embeddings, working with vector databases, building and evaluating RE systems. These aren't niche specialties anymore. They are rapidly becoming the essential foundation for anyone who aims to build intelligent, reliable, and truly valuable applications in this era of generative AI. So, what does this all mean for you right now, today?
Well, hopefully it means you now have a much clearer understanding of how these AI systems actually go from being a brilliant idea or a cool demo to becoming a functional, dependable solution that you can actually deploy and rely on. Think about all the unstructured knowledge swirling around inside your own organization. Maybe it's legal contracts, scientific research papers, years of customer support tickets, messy internal wikis. This deep dive should give you a really tangible sense of how that, unstructured chaos can potentially be transformed, turned into actionable, semantically meaningful data that your AI systems can truly understand and leverage to provide real value.
It's a fundamental shift in how we interact with and utilize information. Keep exploring, keep asking questions, and definitely keep building. You've just taken a massive step forward in learning how to navigate this exciting new frontier of AI.